Cool. So, hello everyone. Ah, internet's bad. Yeah. Um, so yeah, having the recording will help in case people cut out. You lose batteries, lose power, lose connectivity, any of those things. So yeah. Um, so the announcement's coming up. If you haven't turned in, how long is the exam going to be? Similar to a homework? Yeah, it's going to be comparable to a homework. It'll be. I'm going to try to make it shorter than the last exam, just because. Yeah, we got stuff going on. So sound good to folks? Um, I also want to invite everyone come to the Physics Tea tomorrow. It's um, I sent out an email about it, and Dr. DeFree had previously. Maybe I'll post about it on Blackboard too. It's yeah, a good chance just to stay connected with people, check in, see what's going on. Um, we've also started inviting some of the accepted students who are applying who've applied and been accepted for next year, just because a lot of them aren't going to get a chance to do a real tour and visit the campus. So we wanted a chance for them to interact with professors, but also with students. So and then okay, so cool, yeah. Um, uh, yeah, so Friday, quiz. You'll see it's multiple choice. It's open notes, open, and I've told you kind of the focus. I put up, a page of materials just like I did for the previous ones, but you don't have to memorize them. You've got that page of materials. You can work with it however, whatever works best for you. The only thing is, I encourage you to familiarize yourself with them in advance because you get 30 minutes to do the 5 multiple choice questions. And so for that, it's due by midnight. And then I push that reading even farther still. And yeah, I'm going to post the exam. I'm not sure I can get it done tonight. It's the first night of Passover, and I'm still trying to tweak some things with it. But I will get it shortly. Any questions about all that before we get going? Okay, I'll take that as a no or a delay or something like that. So today we're actually going to talk about electromagnetic waves. We introduced the idea of waves in general, and we're going to use some of the stuff that we looked at, but we're going to take a look at them specifically for electromagnetic waves. And so as we, finally got to a couple chapters ago, we've got Maxwell's equations, and that's going to be what governs our electromagnetic fields. So for our waves, we're going to start off taking a look in. I knocked stuff off my desk. Pardon me. We're going to start off taking a look in. Uh, give me one moment to something happened with my pad, and it's really positioned reacting strangely. I think I'm going to make it so. It's really just on the one. Yeah, there we go. A lot better. I'm sorry. So electromagnetic waves. So Maxwell's equations. We're going to look at them just in empty space. So to begin with. So. Whoa. Right. Maxwell's equation is going to be our guiding set of rules. So first off, we've got Gauss's law, but empty space means there are no charges there. So our divergence of E is 0, divergence of magnetic field, that's always 0. Our Faraday's law tells us that our curl of E comes about from a changing magnetic field. And over here, what would normally be the Ampere-Maxwell law, well, if they're empty space, we don't have any currents to act as the source. So the only source remaining is the displacement current, right? The changing electric field. And so if we look at these, this set right here, right, this whole set they're both is four coupled differential equations, four coupled first order differential equations. And what we're going to do is we're going to just do some math on them, decouple them, and from them derive a pair of second order uncoupled differential equations. By couple, I mean the fact that we've got, for example, the curl of E has to do with the time derivative of B, and the curl of B has to do with the time derivative of E. Okay, so to do this, what we're going to do is let's start off with Faraday's law. So for this, right, so that is the fact that curl of E is minus dB dt. Sorry, I didn't leave myself much space here. And what we're going to do is we're going to take the curl of both sides. Right, so let's start with the left-hand side. LHS for left-hand side. So we're going to do the curl of E. Curly. All right. So what is this right here? This is something you could look it up. It's a lot like taking a triple product if you had A cross B cross C. If you remember that from like vector calculus or some other class, A cross B cross C, the acronym for the mnemonic for that is BACCAB. So it would be B times A dot C and C minus C times A dot B. And so we'll write that out this way. It's a little bit more involved with vectors, but it effectively amounts to the same thing. So we take the gradient of and then do scalar multiplication of that operator times this dot product with the operator. So that's a divergence. And then minus, it would be del dot del, which would give us the Laplacian of E right there. So one of the things we know is just looking up at Maxwell's equations right above there is that the divergence of E, that's 0. Right? So we can just rewrite this right here. This is just minus Laplacian of E, like that. All right, so that's the left-hand side. Let's take a look at the right-hand side. So what happens when we take the curl? Shouldn't the Laplacian also be equal to 0? No. No, it is not. And we'll take a look at that with some example functions. Yeah, it is not. The curl, no, the divergence of a curl is always 0, and the curl of a gradient is always 0, but the curl of a curl isn't necessarily 0. Got that? Yeah. You don't have to, that's something we can go back and verify, but for now, yeah, indeed. Just so the curl of a curl isn't necessarily 0. but we had a couple other examples. The divergence of a curl is zero, and the curl of a gradient is zero. And both those you can prove with the divergence theorem and Stokes theorem. Okay, so we got this part right here, and we could take the spatial derivative and the temporal derivative. Those will commute with each other. So we can write this as minus d dt of the curl of B. Okay, oh, and we've got an expression for that. The curl of B, we look up at the fourth one of our Maxwell's equations, the Maxwell part of the Ampere-Maxwell equation is the curl of B there is proportional to the time derivative of the electric field. So what we're going to end up with is we still have that negative sign, and here's those mu naught epsilon naught, and so we have d dt of d dt of E. So we get d squared dt squared, second derivative of the electric field. All right, and so now those two things are equal to each other. And so here we'll take that up here. And so the left-hand side is equal to the right-hand side. And so we can write this as the Laplacian of E. And again, remember, Laplacian is take the second x derivative plus the second y derivative plus the second z derivative. And so this will still be a vector, though, because we have to do those derivatives for each of the components there. So we have minus Laplacian of E is equal to minus mu naught epsilon naught. So let's just drop the minus sign because it's common to both sides. I'm going to put a box around that. That's worth boxing. Right? And we can do the same thing for the Ampere-Maxwell law, too. We'll come back to the box equation in just a minute. Right, so Ampere-Maxwell law is the fact that kind of looks like the wave equation from the formula sheet for the quiz. Yes, right? Kind of looks like the wave equation. We've got a second order spatial derivative and a second order temporal derivative, some coefficient out front. So we're going to interpret all those things right there. The wave equation from the quiz, right, that has to do in general with waves, just one dimensional, right, because we haven't wasn't going to quiz you on stuff we hadn't seen yet. But we're going to talk about taking that one-dimensional equation, turning it three-dimensional. That's an E. Right. I'm sorry about that. The handwriting there. We're in all both sides, just like before. So I'm going to move my pad so it's easier to write over there. So the left-hand side, right, we've got the curl of B. This is curly. Someone's asking a question with a pointer. That's an E right there. Do I need to clean that up? Let's see if I can get to the V underneath it. Nope. 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 Anyways, that's an E. Checked. Okay. Right. So that right there, we've already seen that's going to be equal to the gradient of the divergence of B minus the Laplacian. Laplacian. Sorry. Whew, did I do that? Did the screen just suddenly zoom in for everyone, or does it look okay for you? Looks fine. Okay. I must have hit some weird control. I did something weird because it's making my pad. It's not happy about me writing on it though. Give me a second, please. I apologize. Okay. Can I write now? I think so. All right. Yeah. It's happy again. All right. And once again, we know that the divergence of B from Maxwell equations, that's 0. So what we're left with is just the negative Laplacian. This is starting to look kind of familiar. Right? And on the right-hand side, right, we're going to have the curl of mu naught epsilon naught time derivative of E, electric field, right? And so we can rewrite that as mu naught epsilon naught times the time derivative of the curl of E. Make a substitution for the curl of E. Well, from Faraday's law, we know that's minus dB dt. So we've got a minus u naught epsilon naught derivative of the derivative of B, so d squared B dt squared. And again, set them equal to each other, canceling out that common factor of negative 1. And we get the Laplacian of B is equal to mu naught epsilon naught d squared E dt squared. And hey, look at that. Aside from changing which field it is that we're talking about, that looks identical, right? And so, yeah, like we just mentioned before, the wave equation. This looks a lot like the wave equation, right? The wave equation that we saw before was the second derivative of f with respect to one variable, right? Equal to 1 over v squared times the second temporal derivative right there. So for now, let's just say, hey, well, we can just make a generalization. That's an x right there that you're pointing to. We okay with that? We can make the generalization that our first order or one-dimensional derivative, we can just replace that with a three-dimensional derivative, and we'll do that a little more formally later on. But now just by looking at this, right, by inspection, we can see that mu naught epsilon naught is playing the role of 1 over v squared, right? And so that tells us then that our electromagnetic waves in empty space, right, have a speed, well, okay, it's got to be 1 over and then take the square root of mu naught epsilon naught there, right? And so that's 3.00 times 10 to the 8th meters per second. And that is just appearing from these fundamental constants. It's a fundamental constant of its own, and it drops out of them. And so we call that c. That's our speed of light. So our electromagnetic waves in empty space, at least, where we didn't have any charges present, behave this way. Pretty cool. So we'll take start working with them in just a minute after I take a snapshot. Questions while I'm doing that? This is a good time to pause. Okay, cool. All right, then I'm going to proceed. Let's see some of the properties of these things. So once again, stay simple. We're going to start um, with one frequency. And so that means one wavelength, right? Right. And why are those? Why is that the same thing, right? We know that V. Whoops, wrong thing. Right. V, which is equal to C, right? Also going to be equal to lambda times nu. So we know all the waves have the same speed. And so if we say they all have the same frequency, that guarantees they have the same wavelength, right? Since wavelength determines color, right, we call these monochromatic. So we're going to do a few other things. So why is it okay to just work with these monochromatic waves? Well, like we saw before, we can build other kinds of waves, not just, we can build changes in their amplitude out of a sum of a bunch of different frequencies. And even later on, once we start introducing more than one direction, we can build up other types of waves out of going in a variety of directions. We can build those out of plane waves too. So it's a good place to start. The math is a lot simpler. What else are we going to do? We're also going to have them all going in, like I said, the same direction. And like we often do in physics, when we've got one special direction, we'll call that direction Z. And so the other thing is, so they're all going in the same direction, and we're going to say that as you move to different locations in X and Y, we're going to say that there's no change in them. So even if they're going the same direction, their amplitude doesn't change as you move to different X and Y positions, right? So we could try to draw a picture of this as best we can. Whoops, it really doesn't work if you don't use the right tool. So that's the Z direction. That's going to be my X coordinate. There's my Y coordinate, right? A little bit different view than we're used to, but I want to have these going off to the right. So we're going to have our waves, right, waving in the Z direction, right, and traveling that way. And all of them will look the same even as you vary X. This is my attempt to make it all look the same. They're all going like that. And that's repeated, make copies of that in the Y direction too. It would get kind of sloppy for me to draw that. So one of the things we can do, so that's a lot to visualize. Another way to visualize our waves is we can connect points that have the same phase. So as I try to draw this again, what that's going to look like here. I'll do that in orange up here. I think we touched on that in Fund 3 or Fund 2. Right, these all have the same phase. That happens to be, for if this is the cosine, that would be a phase of 0. Here would be like a phase of pi if we're talking about cosine, right? Again, here's 2 pi, etc. So if I do this, right, what have I got? And the same thing's happening in the y direction too, right? So what we get are basically planes right? So we get these planes, and so we call these things, right, plane waves. So let's write these waves out for our electromagnetic waves. So for we know that we're going to have something, our electric field will obey the wave. So everything we talked about before worked just fine. It's a vector, though. And we also remember that it's a lot easier to deal with these things when they are still confused about the planes. Okay, so I've connected all the points here. I'm going to go back and write on there. Thank you. Thanks for asking. So this right here, this corresponds to a phase, for example, of 0. This here corresponds to a phase of pi. Right, and they look like straight lines. Remember, because I've only drawn them as I vary x. So if I were to make copies of these, so this is extending in the y direction too. So those lines that I'm drawing at 0 and pi, are these multiple waves? Well, it's all one wave, but I can't draw it everywhere, so I'm drawing, multiple versions of. I'm mapping it out at a bunch of different points, but this is a field, so it exists all throughout space. But I can draw it filling all of space, so I just draw the amplitude of it multiple times. Yes, and that's a really important thing. These plane waves, to really be true plane waves, they're going to extend to infinity in all directions, so in x, y, and z. If they don't, then they're not really plane waves. So pause and say, well, I've never seen a wave. So the same magnitude of E all along a plane, and then also the same magnitude of B all along a plane. E and B don't have the same magnitude as each other. They don't have the same dimensions as each other. But the same magnitude of E all the way along the plane. Same magnitude. So we're going to come to that. How does the E and B relate to each other? We're going to come to that. But yeah, so one of the things you might say was, well, this seems kind of like, pretend. Like, I've never seen a wave that extends out to infinity, like, whether it's along the direction of travel or perpendicular to it. I've never seen a wave that goes out to infinity. And yes, exactly that. That is true. This is an idealization, a mathematical idealization. And so there is really not any such thing as, in reality, as a truly monochromatic wave, because we can have something that is, really very narrow frequency, but it hasn't been oscillating forever, and it won't continue to oscillate forever. So it's got to have some range of frequencies in order to have a start and stop. A true monochromatic wave has to continue forever. And similarly, like we're saying that the waves are all going in the z direction, and if they don't actually extend all the way out to infinity in the x and y direction, that really means that you somehow have to have some combination of waves going in that have some x and y components too, in order to make the finite extent. But this is, we can start out and imagine these things go out forever, right? And say, well, okay, we'll deal with the complications of reality as we come to them. And again, we can build everything out of combinations, linear combinations of these monochromatic waves and also of plane waves. So this thing right here, right, it is a vector, but oops, I'm going to draw and keep it in the same color. But not only is it a vector, but we're going to write a complex function. So I've got to write the vector symbol and the tilde, right? Vector and then tilde to show that this is the complex function we're going to use to represent it. So we're going to have an amplitude, and that amplitude is a vector too. and it's a whoops, that didn't come across right. It's a complex amplitude. So it's got the real amplitude and the phase factor, right? And then we have an oscillatory term. And then a similar kind of thing right here, right? We've got B, right? And so notice I'm making this a function only of Z and T, right? Because we said that there's no variation in X and Y for these plane waves. So we're going to write out a complex vector function, complex vector field. It has a complex amplitude. So it's got an amplitude, a vector amplitude, and also a phase constant. One of the questions we might have is, how does the phase constant for B relate to the phase constant for the electromagnetic wave? That's something we'll check out in a moment. Yeah. Why is the amplitude a vector, right? Because the field itself, right, is a vector field, right? And so the oscillatory term just causes oscillations, and it's not pointing up and down. It's changing the magnitude and phase as we go along, right? So in order to get a field, we got to have a vector amplitude. If we want, what we're going to do oftentimes, though, is we're going to separate that out into a scalar amplitude and then a vector polarization, a direction. Like, so basically, we'll take that and separate it out. So the wave amplitude is the vector, but we can then separate that further into its magnitude and direction. So again, these complex functions, though, is just something that we introduced as a tool because it makes the math much simpler, even if complex numbers are initially, a bit of a challenge for us. So what is you might say, well, what's the electric field? I don't, what is this weird complex thing, right? The complex thing is a calculational tool. Really, we've got an electric field, right, that is real, right? I don't know what an imaginary electric field itself is, right? And so that is the real part of the complex function. And the same thing over here, our actual measurable, observable magnetic field is the real part of that complex vector field.
Professor,
Yeah.
I know this is from a few classes ago, but I just thought of it. Why is there an imaginary part to this at all?
Yeah. So the first answer is we could get by without the imaginary part right here for a very long time. We'd have to do like crazy trig identities and stuff like that, right? It is a useful tool to make the calculations a lot simpler once you get comfortable with imaginary numbers. So that's the first answer, right? Another way to think of it is this, if you, and why, or, well, and one of the questions might come, well, why are imaginary numbers, why is this complex version of this the appropriate tool? Why not pick some other tool? And so that comes from the fact that e to the I theta is equal to cosine of theta plus I sine theta. So e to the I theta produces our cosine of theta that we're looking for, that oscillatory behavior. If you make a plot of the complex plane and plot out e to the I theta as theta increases, it's going to trace out that unit circle in the complex plane. And then you can take just one part of it, just the real part, and you get the cosine part that oscillates. So it produces oscillatory behavior. It contains the cosine without actually having to do trig itself. You can just work with multiplying and adding exponentials, which actually, again, turns out to be oftentimes a lot easier to work with. Does that help out there, Derek? And everyone else too?
Yes, thank you.
Cool. All right. So part of the answer to it is, okay, yeah, I explained it there, but the other part is trust me, right? It does. It's a useful way to do it. So, all right, so we're taking what we learned before and we're saying, okay, yeah, we can do that for electromagnetic waves. It's confusing, a little bit more confusing because we're talking about vectors, not just a scalar value. So let's actually take a look at these things, though, because we're combining electromagnetic waves and Maxwell's equations. We saw that Maxwell's equations produce the wave equation. And so one of the things we can say is that if we have these oscillatory, I'm sorry, here. We get these oscillatory solutions to Maxwell's equations. All of those will be solution to the wave equation. But the converse actually is not true. That's my abbreviation for solution. Solution to the wave equation. If it's a solution to, if we have a function that's a solution to the wave equation, it doesn't automatically imply that we've got a solution to Maxwell's equations. So another way to say this is Maxwell's equations are more restrictive. There's more going on in them. Right. Let's see. We can learn other things though about taking a look at using Maxwell's equations, right? So this is actually an example. So and specifically, that's EN, electromagnetic wave properties, right? So let's look at an example of, we've seen that we can have different kinds of waves, right? We can have longitudinal waves, you can have transverse waves. Let's see what we can do with electromagnetic waves. And we've also, in your other classes or in readings or whatever, you've seen this, the punchline is that we can't have all kinds of waves with electromagnetic waves. So let's take a look at these things. So we've got, from Maxwell's equations, right, from Gauss's law in empty space, one of the things we know is that the divergence of E is 0 because there's no charges there, right? Right, for our plane wave, right, we know that there's no X or Y variation. So that means that, well, okay, take dE, the X component, oh, that's supposed to be a tilde. Take the X derivative of the X component of it, and it's going to be 0. You take the Y derivative of the Y component, that's going to be equal to 0. And actually, in fact, since there's no xy dependence in e to the I kz minus omega t, right? We combine that with the fact that there's no overall x or y dependence to those components, then we can actually say that there can't be any x or y dependence to their amplitudes either. Right. Right. So where am I going with this right here? Right. We've got the fact that there's in the plane waves, there's no x or y dependence to the wave amplitudes, their x and y components. So with the fact that the divergence is equal to 0, well, what we've just said is that the x and y terms in the divergence are 0. So that means that the z term has to be 0 too. And so that would be dE dz of the z component equal to 0, right? So, well, let's take a look at this. This derivative right here, right, is going to have, well, we get the you take that derivative, and we'll get this complex amplitude right here. Oh, the z component of it. And then we take the derivative and we get ik e to the, I'm sorry, we get the ik coming down from the exponential. Right? So all that was equal to 0. So what that tells us is that that amplitude itself so what is that telling us right here? Ooh, I ran out of space. I'm going to actually work a little bit to the left. Right? So there's no longitudinal component to this electric field wave. And we can do the exact same thing, right? We got this from the divergence of E was equal to 0 and the fact that we have plane waves going in the z direction. So we can do the same thing for the magnetic field because the divergence of B is also the same, similar, is also 0. Right? So it's similar for B, right? And so what that tells us overall is that our electromagnetic waves are only transverse in empty space, right? This was all in empty space. Okay, so again, looking at Maxwell's equations, we have this additional constraint that's not present in general for the wave equation, in that we can only have transverse waves in empty space. Here, I've run out of space absolutely on this, so I'm going to snapshot it. Okay, so we've got that right there. We can find out more, right? So we just learned that they're transverse. Let's take a look at what else Maxwell's equations tell us. Oops. So one of the things we have is the fact that we've got Faraday's law, curl of E minus dB dt. So let's, oh, okay, I erased my equations. Let's write them down again. So our oops, not that, that's jumping the gun. Whoa, it just did it again. All right, there we go. Our complex electric field, that's supposed to be a tilde. That's supposed to be a tilde. Keep smoothing it out. And all right, so this is just a reminder of what the functions are. So now we can take these derivatives right here. So on the left-hand side, we do all the, it's a curl, but there's only X and Y components present. And so we have to take when we take the curl of these things, but they're only varying in the Z direction. So we're going to end up with X and Y things. We'll have from taking the derivative of E, we're going to get an IK, but I'm going to factor out the I. And then taking the temporal derivative of B, we'll get minus I omega. So and then here we're going to, so I've factored out the common I for both of them. And I've also, whoops. So those are subscripts there, X and Y. So what's different between the two different components equations right here? Remember the curl, you get a minus sign depending whether you're doing the derivative with respect to X of the Y component, that's going to be positive. The derivative with respect to Y of the X component, you pick up a minus sign. That's the difference between them right there. So we've got this thing where the Y component of the electric field is related to the X component of the magnetic field and vice versa right here. And so one way, compact way to write all that right there is we can divide through by omega on both sides. And so we can say that our magnetic field's amplitude will have a factor of K times omega. And the other way to get the fact that, yeah, just a second, Harry. The other thing we can get out of this is the fact that if we have only an X component of the electric field, we'll have only a Y component of the magnetic field. Now, if we have only a Y component of the electric field, we'll have only an X component of the magnetic field. And so what that's saying is it's always at a right angle to each other and a right angle to the direction that it was going, which was Z. So I'm going to write it this way. This is the vector. Oops, and this is, I'm going to write this as the vector. All right, Harry, what's up?
I'm good with you under the assumption of those two equations that you've put a curly bracket left of, but I missed something how you got the relationship between the subcomponents the equality between those?
Sure, sure. So here, yeah. So I skipped a step. I skipped a step. So what I'm doing first right here. So this is. I should have explained that better. Yep. So here, let's do this. This is the x term right here, and this is the y term. You're saying, well, why is there a y right here? This, remember what we're doing. This is d dz of the y component of e will give us the component of the curl in the x direction. So d dz of e sub y with a minus sign is part of the curl of E in the x direction, and d dz of the x component of E points in the y direction in the curl. So this is the x components of here of right. But the fact that we've got a curl, that's why we end up with the y component of the electric field appearing in the x component of Faraday's law equation. That started with why we've got two parts and why there's the mix. And then on the left side, when we took the derivative with respect to E, I'm sorry, the derivative with respect to Z of E, we pulled down an IK. That's why we've got a K here. And when we took the derivative with respect to time of B, that pulls down a minus omega t. I'm sorry, minus I omega t. And so that's why we get an omega on this side. And we cancel out the common factor of I from each of the derivatives. And then, yeah, one of them we get a minus sign in the order in the curl, and the other one we don't. Do you have to reproduce that? No, right? But we're showing you that part of what we want to see is that this system produced by Maxwell's equations tells us all kinds of information about the properties of the waves. Right? So, for example, right here, this right here actually, besides giving us an exact relationship between their vector amplitudes, it tells us several things. So first of all, right, it tells us that B and E, well, they're just a multiple of each other. No complex numbers involved in the multiplication, right? They're both complex functions, but we're multiplying them by a real vector and by real K and 1 over omega. So that tells us that they have to have the same phase, right? It's just a real multiple, so it's only when you multiply a complex number that you shift the vector in the complex plane. So they've got the same phase, right? The other thing is that they're always orthogonal to each other. And they're also both orthogonal to the direction of propagation, the z direction. Right? Oh, we saw that before, but that's now embedded in this statement right here. So, and we also have, we can write out something about their amplitudes. B naught is K over omega. Whoops. Now this is the real amplitudes, right? We're taking the real part of this. That doesn't make sense what I just wrote. Pardon me. Oh, one moment, I'm going to sneeze. Pardon me. allergies.
Bless you.
Cool. So, thank you. So we've got this relationship, and actually, right, K, omega, those are related too, right? K over omega is 1 over v, and v, our speed of our wave, is c. So that's going to be really, really useful. So we've got the fact that they've got the same phase, and they're perpendicular to each other. And now we've got a very specific relationship between their amplitudes. So the magnetic field amplitude is 1 over c times the electric field amplitude. That's nice and simple. So yeah, I don't know. Those are all important points right there. So we can try to draw this here. Yeah, let's do that. I'm going to try. Oh, I thought I changed the color. So again, for the x direction, the z direction is the direction we're going to go to the right. Oops. So this has to be y. Notice, yeah, it's a right-handed coordinate system. Let's draw the electric field first. So I don't know why I did it crushed in there. I was thinking I was going to make it longer. You know what? I will. I am going to make it longer. And there's nothing you can do to stop me. Oh, wait, there is, but. All right, so my electric field I'm going to do in blue. Let's start off here. Let's have the electric field along the x direction. And so if it's traveling in the z direction, that tells us then, because B has to be perpendicular to both those things, that it's got to be along the y direction. That's parallel to the two lines. So here, well, that just becomes a simple sine wave in terms of its amplitude. So really, we should be drawing in the vectors or whatnot, right? So yeah, they go. Right, so as we move along in z, the field gets stronger and stronger and stronger, and then weaker and weaker and weaker. And then we could make a copy of this, of course, along the x direction or along the y direction too. And I can do one thing right here, right? The maximum amplitude that this reaches right here, right? That is E naught right there. And then let's do something similar for B. So B is going to oscillate in phase as well. It's going to point in the y direction, right? So I got to do this more in perspective because y is foreshortened. All right, and so these point in the y direction like this. I'm trying to draw them parallel to the y-axis still. And then same thing. Not quite right. So that's my amplitude B naught, which is going to be E naught over C, like that. So this is at one particular time, right? So this is and so as time passes, though, these waves will propagate off to the right. And again, we've got copies of this happening, the exact same thing happening at every single point along the x-axis, and every, as you move around in x and as you move around in y. You like that? The cool. Really? Are you just messing with me? Uh, ah! All right, but Derek, you're expressing an unhappiness about this. Is there some part you don't like in particular? You're teasing also. I gotta, this whole nuance and sarcasm over online platforms. I just don't have it down yet. Cool. All right. So let me take a snapshot of this here. Okay. All right. So yeah, last few minutes. What we're going to do is we're going to take this and bust out of our one-dimensional, like saying, hey, let's just talk about going in the z direction. We're going to bust out of that. We're still going to talk about monochromatic plane waves, right? So here, let's put this right here. All right, that's what we're going to do. Generalize it to monochromatic plane waves in any direction. So what we're going to do is to talk about which way it's going, instead of just saying, hey, it's going in the z direction. We're going to talk about which way it's going. We're going to introduce what's called a propagation vector, but actually is more commonly known as the wave vector. Right? Propagation vector in some ways is more descriptive. Wave vectors, I don't know. But what do people call it? They always wave vector. And so that is denoted like this, a vector, right? And so first thing is, we already used that symbol. Well, yeah, actually it's referring to the same thing. Its magnitude right here is k, right? Which is 2 pi over lambda, right? So the magnitude of the wave vector is the wave number that we're familiar with. But the direction is the direction of propagation. So that's kind of cool. It actually doesn't just tell us which way it's going, it tells us something about more about the wave, specifically its wave number. So before, right, where did the wave number appear? When we were doing it one-dimensionally, we had e to the I z minus omega t. So now what we're going to do is we're going to replace that with e to the I So this can work and tell us what's going on with the wave for any position in space. Okay. So for example, when we were doing this previously, when we were saying we were going in the z direction, right, we had, when we were doing this in the z direction, previously, right, what we did was that. And so then, for example, then e to the I k, well here, yeah, k dot r minus omega t. Well, k dot r will get is equal to, actually, I want to just get rid of this for right now. We're short on time. I don't want to write all that out. Let's just write k dot r in that case, right, would be equal to kx times x plus ky times y plus kz times z, which was just equal to kz times z, and that was equal to the magnitude of k in that example, right? So that's why we were able to just do e to the I kz minus omega t. This was a special example of this full three-dimensional version when our k vector was just the wave number times z hat. Oops, and this is supposed to be a plus. Cool. So how do we write this out all the way? And this will be where we conclude. We can write out our electric field vector in complex form, right? And the complex function carries along this extra bit of extraneous information in it so that we can just take the real part of it all. We've got a complex amplitude. I'm not going to write it as a vector amplitude. I'm going to write it, that's just a scalar amplitude. We'll include the vector part in a moment. So we've got the e to the I k dot r minus omega t. And then I'm going to include a vector direction for the field. So that thing right there, that's going to be our polarization vector. Which way does the electric field point? Right, we talked about how we could have different polarizations when we were doing just the z propagation. Same thing happens now, except it can be in 3 dimensions. We've got a function for complex function for our magnetic field, and the amplitude is just 1 over c times the electric field amplitude. Yes. Is the polarization? No. So the polarization vector is, I'm going to write a couple things down in a second about what the polarization vector is. Just a second. All right, and I'm going to write this as e to the I k dot r. And then here, right, we're going to get, it's got to be perpendicular to both the direction of propagation and to E. So that's one way to write it right there, is we take the cross product of k hat, so the unit wave vector, take the cross product of that with the polarization vector, and that guarantees that B will be perpendicular to both E and to the direction of propagation. And we can actually just write this overall as 1 over c k hat cross E. Because notice so much of B is already included in E in that as a function. Right? And so the one other restriction, so here's one thing we have to say, with our polarization vector has to be perpendicular to the direction of propagation. Whoops. Transverse. Sounds Russian. Cool. So we've got E dot K is 0. So another way to say this is E dot K hat equals 0. B dot K hat equals 0. And E dot B equals 0. Someone's asking, is this is a C, the 1 over C right here. Sorry, I can see my thing. That's a C. Cool. So it takes some getting used to this K dot R, right? Because we're taking the dot product of vectors, but that gives us just a scalar. So that's part of just the phase of this complex exponential. And the easiest thing is to kind of relate it back to the one-dimensional case. That's what feels, helps me interpret it. But we've got this relationship right here. In particular, right here. Sorry, one more moment. Right, this was B, complex B. That part right there is pretty useful too. And again, the fact that it's transverse. Okay, I'm going to snapshot this because I'm over. Dang, I'm sorry about that. Did not mean to do that. So I'll say, if you've got questions, ask me. Try the homework. Ask me questions with that. Let me come back. What was the question? Thank you. Thank you to everyone. Feel free to reach out to me by email at any point in time. Let me know. I won't necessarily respond at any point in time, but thank you all. Appreciate it. See you at tea tomorrow. Extra credit. Take care. Did it have static the whole time? On and off. Okay. I think I'm going to I've got this extension cable to help me so I don't get tangled up with other things on my desk. I'm going to get a better quality one maybe. I appreciate that. Thank you. All right. I will see you later. Take care.